Hey there, I'm Kevin Reynolds, and this is Screencast assignment number 4, where we're going to look at linear free energy relationships, or LFERs for short. So there's going to be a couple of things that's going to go into this, but what we're going to start off with is kind of what this graph actually looks like. So here's one of our LFER graphs. Kind of to note is we have energy on our y-axis and the reaction rate or coordinate on our x-axis. Now, two things kind of seeing in the graph is we are going to be our delta G double dagger of H, which is going to be our reference reaction, and delta G double dagger of X, which is going to be our varied or our substituent reaction. The biggest thing to note in this is the activation energies themselves and how they're actually different, with X being less than H, our reference. From here we can slide over and we can look at the actual equation that's going to relate these. Now, I kind of mentioned this reference thing and whatnot, and what that actually is what the X position is in this molecule itself. So it's para-substituted to the actual site that's going to be doing things or changing, which is up here. So that's what both of these come from. Now, one thing to note is that it's actually going to give us a negative, since we're going to take something small minus a larger thing, which is where this equation comes in. Now, we're just going to be taking our negative delta G double dagger X, whatever the case be, divided by some numbers, but it's going to give us two factors, rho and sigma. What our rho actually is the relationship to kinetics, and our sigma is our thermodynamic equilibrium relationship of X. With a mention of reference sliding back up, this H and this X, what we kind of want to look at is how it alternates. So this X, what we're going to do is actually put different groups in. One big thing to note is we can do it with withdrawing and donating electron groups. Two rather common ones are going to be our NH2 as our donating group and our NO2 as our withdrawing group, and how those actually play in. So I'm going to slide up and go over the donating one first. So what we kind of see is how when we throw in NH2 into that X or para-substituted position, we get this kind of pushing of electrons from down here up into this bond, which rotate up, and then all the way up onto this bond or this carbon right here, which you can kind of see right up here, which is going to form a negative bond or a negative charge, and our NH2 is going to hold this positive one, giving us a net dipole up. Now this is beneficial because anytime we have a positively charged thing coming in, kind of where this chlorine or any of these methyl groups are, we get this stabilization from a negative charge. However, one problem or thing that comes up with electron withdrawing groups is a difference of charge. This difference of charge is seen when we use NO2, or a withdrawing group itself. How that works, kind of in reverse to the last one, is our bonds are going to shift, or our electrons are going to shift all the way down, and we're going to get this double bond to N, which is going to create a double negative down at the bottom with the positive up top. Now, like I mentioned before, we kind of wanted that negative up top to take on whatever positive is joining. Getting a little more in-depth, we're going to get this relationship. So we're going to see this kind of rate of the X divided by the rate of the H with the log 10 in relation to these actual factors that we have. Now, from here, what we can do is take a step back and look at what rho is actually going to show us. Now, rho is going to give us some ranges. So we're going to have a value at rho. So anything bigger than 1 in rho is going to give us a more sensitive thing in relation to our reference. Where equal to 1 is our reference itself, anything between 0 and 1, less sensitive than the reference, and then anything that's going to give us an opposite relation is anything that's less than 1 with rho. Sigma, on the other hand, or also known as the Hammett parameter, as Louis Hammett is the one who kind of coined this, was looking at the relationship strictly to benzoic acid. He found values, like I mentioned, kind of substituted straight to benzoic acid and how that would affect with the withdrawing and donating. So in reference to our reaction as before, we see this phenomena happening. Now, I drew this transition state to show that there's actually going to be this positive charged form, which means at this point right up here where this red dot is, we want to look at getting a negative charge to stabilize, which is where a donating group wouldn't be as good. As this donating group would be better, we're going to get a negative rho, due to the fact that a positive rho, indicative of a better reference, is going to be in relation to a withdrawing group in regards to benzoic acid. Therefore, we're going to get a negative rho for this reaction.